Alright, so yesterday we started to talk about arc length, how we can find the distance traveled along a curve, not necessarily a straight line. And we developed the arc length integral or formula that we can use to help us determine that length. Can we refresh our memory? And I'll write it down at the top of page 33 so we can use it. Do you remember what it looks like, what it involves? There is a square root, yep. 1 plus the derivative squared dx from a to b. Okay, so we're going to use that integral today as well. We're going to take a look at some interesting things, though, about arc length in terms of equations that have something weird going on. So if you take a look at the first one, we're going to find the arc length of the curve, the cube root of x, on the interval from -8 to +8. So if we're going to use this formula, we have to first figure out the derivative of the curve or function that we're given. So let's go ahead and take the derivative of the cubed root. You can think about that as x to the 1/3 power. Okay, so power rule, subtract 1 from the exponent. Instead of a negative power, you can make it positive by moving it to the denominator, all that jazz. We can get that derivative, right? Okay, so do you guys see anything interesting or special or noteworthy about that derivative? Any value for x that might be an issue? We're thinking 0, right? And what are the bounds that we would be using for our length integral here? Yeah. Which includes 0, right? We're going from -8 to +8. So we have to be careful, because if our slope is undefined, okay, we are dividing by 0, we either have a vertical tangent, a sharp point, a discontinuity, anything like that graphically. So let's go ahead and examine. I mean, maybe some of you already know which one of the 3 possibilities it is, but let's go ahead and examine this graph of the cube root of x. So in y equals, you can clear out anything you have in there. We'll type in x to the 1/3, which is the same thing as the cube root of x. And let's go ahead and change our window. We're going from -8 to +8 on the x-axis. Maybe you want to count by ones. Maybe on the y-axis we'll go from -5 to +5. You can make those values anything. So if you hit graph, we're going to have this cube root function, and notice how at 0 we have that vertical tangent. If you were to draw a tangent line, it would be completely up and down. Okay? But in terms of the arc length, we should be able to calculate, if you were to walk across that graph, you should be able to calculate how far you actually walked. So there is a distance to find. The issue is right here in the middle where the derivative doesn't exist. So we kind of got to be strategic at this location, okay? Because if you take the integral of something where the derivative doesn't exist, your calculator is going to pop up like an error message. So how might you think we can still use this integral formula, but being strategic on how we evaluate it at 0? Yeah. Mm-hmm. Great idea. Okay, so we're going to break up the integral. We're going to have 1 plus, let's see, if we square this derivative, 1 squared would be 1, and then if we square the denominator, we would have 9x to the 4/3. if you square an exponent, you multiply the exponents together, so 2/3 times 2 would be 4/3. So we're going to actually have two integrals. We're going to break it up at that 0 spot. Okay. But the thing is, we cannot write 0 there because we would be including that value that's an issue. So what number might you want to put there that's not 0, but really, really, really close to it? How about like 0.00000? Maybe we'll do 1, okay? I mean, we're trying to get as close to 0 as possible, right? Now, this first value would have to be negative because we're approaching 0 from the left, okay, the negative side, whereas the other value would have to be positive. Okay? So on the calculator, let's go ahead and see if we can actually do this. Now, the calculator is only capable of doing so much. So maybe this value we picked is too close to 0 for it to actually use. If that was the case, we'd have to chop off a few zeros. You're just trying to get as close as you can to that vertical slope, but so that it's not an issue. Okay? So on your calculator, we'll do math 9, -8 to negative point, how many zeros did we have? 1, 2, 3, 6. 1, 2, 3, 4, 5, 6. And then we're going to type in our function, square root of 1 plus. Now, your squared derivative is a fraction, so make sure you put the denominator of that fraction in parentheses. Okay, so we're going to need 9x to the 4/3 in parentheses, and then arrow over so you can fill in your dx. So that's your first integral. You could do one at a time and then add the values together, or you could just type in the next one. It's not like in the 6 zeros? Okay, maybe let me delete that. It might take a while. It might take a while, because you're trying to get as close to that vertical slope as possible.
Oh, there we go.
Okay? It might take a while to think. We'll play some Jeopardy music. All right, 8.6256 or 7, something like that. All right, 8.625, maybe we'll say 7, okay. Go ahead and you can type in the other one. If you want to hit second entry, it'll bring up the same exact integral you typed in, but you just have to switch the bounds. Now we'll have 0.000001 down below. And then we can delete the top bound to make it 8. We'll have some more Jeopardy music. Same thing, okay. 8.6257. So if we add those together, we'll get 17.251, roughly. Okay. Now, in terms of your calculator, okay, I'm not saying that you'd have to do this because it would be kind of time consuming, but we used 6 zeros, right? We should technically try 7 just to see if the calculator could handle it. And if it could, then we would try 8. And if it handled that, we would try 9, because we want to get as close to 0 as possible. So the actual arc length is going to be very, very, very close to this, but depending on the capabilities of your calculator, how accurate or how close you can get to 0, these last few decimal places might change. Okay, so realize that we could get a little bit more accurate, but for time purposes, we're not going to do that. Does that make sense? Okay. Let's go ahead and check out 4. Find the length of the curve from -4 to +4. This one's a little different because we have an absolute value in there. We did not cover derivatives of absolute values last year, but I do give you the derivative or the slope of an absolute value for us to use. So if we found the derivative, we'd have 2x, and then you keep the coefficient of -4. The derivative of an absolute value is the absolute value over x, and then our last derivative would be -1. So in terms of our length, we would need the square root of 1 plus this whole derivative squared. Our bounds technically should be from -4 to +4, but take a look at your derivative. Is there an issue somewhere? It's at 0 again, right? Because there is a portion where we would be dividing by 0. So it's either a vertical tangent, sharp point, discontinuity, something like that. Okay? Maybe we'll check it out graphically. So in y equals, let's go ahead and type in the original function. We'll have x squared minus 4. Do you guys know where an absolute value button is? What's that?
Just go to catalog and it's the first one.
Or you could do that. Okay, so catalog would be the 0 button, and it's blue, and it's the first one, ABS. Another way you can find it is hitting the math button and then going over to number, and it's the first one, ABS. So you have different methods there to find the absolute value. So 4 times absolute value of x divided by x, or no, we're not doing that yet, sorry, that's the derivative, minus x. Our window, we can go from -4 to +4 based off the bounds, and maybe we'll use the same -5 and +5. We might be able to change them, but who knows. Alright, so at that location of 0, it looks like we have a sharp point in this case, not a vertical tangent like the last one. So notice how we should be able to calculate the distance we are walking, but we're going to have an issue at 0 in terms of the integral because the derivative doesn't exist there. So we're going to have to break this one up in a similar fashion. We're going to get as close to 0 as possible without actually being 0. So maybe we'll use the 6 zeros again. And we'll use our calculator to find those arc lengths. Alright, so I typed mine in all at once. You could certainly do yours individually. Is the calculator being friendly to us today? Maybe. Okay, so we could be more accurate. We would have to test if we could get closer to 0 with more zeros in those bounds, but it's going to be roughly around 19.556. Checking out? Good. All right. So let's take a look at some other ways that functions might be represented in order for us to figure out some arc lengths on some intervals. If you take a look at number 5, the equation they give us is not necessarily solved for one of the variables. All the other ones we did said y equals, which was really easy for us to then find the derivative. Notice how in this case it doesn't explicitly state y equals or x equals. So this is when it's kind of nice because you have the option to choose which variable you want to set it equal to. So we're going to do both just to show you how it shouldn't matter, okay, because the arc length is the arc length. The distance is not going to change. It's just how you want to approach your derivative. Do you, or not, your integral rather. Do you want a dx integral or do you want a dy integral? So let's check out the different ways that we can solve this equation for a variable. I think the x is the easier one to get by itself. If you get rid of the squared, we'd have to square root both sides. Can we kind of clean that up though, perhaps, a little bit? Think about how the square root is the same thing as a power of a half. Yeah. Uh-huh. 3/4, yep. 3/4 power. You'd multiply the powers. Yep. Good. Okay, so let's go ahead and maybe solve for y in the other case. Let's see. To move over the power of 3/2, let's see, the division of 2 is symbolizing a square root. So if you squared both sides, this would be x to the 4th. But then we have to get rid of a power of 3, which would be a cubed root, right? Which as a power is 1/3. So we would have a x to the 4/3 as a result if you move over that power. Square both sides, the 2 becomes a 4. Cube root both sides, the 4 now becomes a 4/3. You're dividing by 3. And then we can just add over the 1 that's left. Okay, some of you may have to do that in steps, okay, but in the end it would look like that. Okay, so let's check out our two arc lengths perhaps here. So arc length 1, maybe we'll do a dx like we typically do. They tell us the interval is from 0 to 8. And we're going to need 1 plus the derivative squared. So with your y equals equation, if we took the derivative of it, we would have 4/3 x to the 1/3. Subtract 1 from that power. Let's check out the other one. Okay, if we wanted a dy integral, how might we figure out the bounds on this case? Because we're no longer measuring on the x-axis from 0 to 8. Now we've got to measure the y-axis, beginning and ending point. What do you think? Yeah. Yes, so we're going to take the 0 and the 8, and we're going to set them as x values, or you can plug them into your equation to figure out the related y value. So if we plug in 0 for x, this whole equation would equal 0. If you moved over the 3/2 power, 0 to any power is still going to be 0. So when we add the 1 over, the new lower bound is 1. And now let's test out the 8 value. If we plug in 8 for x, let's see, 8 to the 4/3. Do you want to raise 8 to the 4th power, or do you want to cube root 8? All right, so cube root of 8 is 2. 2 to the 4th, 16 plus 1, 17. So your new upper bound is 17. So we need 1 plus the derivative squared. We're going to go ahead and take a look at the other equation we had, because we need it in terms of y. If we took the derivative here, looks like we kind of have a chain rule, because we have an inside piece. So let's bring down the 3/4. We're going to keep the inside y minus 1. New power, if we subtract 1, would be negative 1/4 times the derivative of the inside, but the derivative of y is just 1. So we need all of that squared. All right. So let's go ahead and check out which, the arc length should be the same in the end. Go ahead and make sure that you can find the same value as you type it in your calculator. So you have options, but notice how when you go ahead and evaluate, or you write those integrals, the dx integral is a little bit more nicely presented perhaps than the dy. I'm not saying that's always going to be the case. Sometimes the dy might look a little nicer. Okay, but at least you have options. Does it work out either way for us? We get the same thing? Okay, so if it's not explicitly solved for a variable, you can choose which one you would like. Either way, it's still going to check out. All right, one more example. So on the back, we kind of have this word problem scenario in terms of finding the arc length, so we're approaching it from a different path here. A manufacturer of corrugated panel roofing wants to produce C panels. I have no idea what these are, by the way. C panels that are 28 inches wide and 2 inches thick. So I guess what they do is they take a flat piece of metal like this, and they use some type of machinery to squish it. Okay, so it looks like this, like the, what are they called, the shingles on a roof. So the profile of the roofing takes the shape of the sine wave here. So that would be the equation of that portion, because notice how that's where the wave is. Okay, I saw you guys doing that. So what we're going to do is find the width, which is essentially, if you were to, again, flatten that panel, it would be how long the sheet was actually before you squished it. So we're going to figure out how wide does it actually have to be so that when you do squish it, you squish it down to 28 inches. So this is technically an arc length question here, because you're trying to figure out if you start here and end here, how long is that wave, which is representing how long the sheet was before you squished it. Okay, so our arc length, let's go ahead and write in our general setup. We got to fill in the missing pieces. So in terms of the bounds or in terms of the function piece, yeah.
Bounds are
0
0 to 28.
to 28, yep. We start at one end and we know that the other end has to be 28 inches long. So 0 to 28. And then what about our derivative piece? Okay, they give us the equation of the curve we're trying to find the length of. So all we have to do is take the derivative of that curve. Derivative of sine, cosine, keep the inside quantity, and finishing off the chain times the derivative of the inside would be pi over 7. So we have pi over 7 times cosine of pi over 7x. And we got to square all that in our integral. Okay, so calculator question. Let's go ahead and figure out the original width of this sheet. Make sure you're in radian mode. We're using trig. They're very close approximations, yeah. 29.361. Thumbs up. Perfect. All right. So that's it for this section. Homework due Friday. Okay? Bring in questions tomorrow if you have them. Bring in questions on Friday if you have them. Okay?